Okay, so today we're going to talk about, we're going to talk about two types of reactions anyway, mostly, which are formation and decomposition, all right? But types of chemical reactions, chemists classify reactions because it allows us to predict the outcome of many chemical reactions just by examining the reactants. We will be examining 5 types to go through. So today we're going to do formation, decomp, okay? Then we're going to talk about combustion, and then single and double replacement reactions. And it's important to be able to kind of look at the reactants and decide what's going to happen. All right. So that's kind of what we're doing here. All right. Now, I know this isn't the next part here, but just so you kind of remember here, a couple things. Elements that appear on their own. Okay. So if I was taking, for example, copper or magnesium or calcium, those elements are neutral, yes? Okay, there's no charge on them because they are neutral. And because they're not part of an ionic compound, they are neutral, all right? And I'll show you that when we get to our first example. We'll spend some time on that. Metals that appear on their own are monatomic, for example, magnesium. Non-metals can be on their own, for example, carbon, okay? Silicone could be on its own. I don't know, arsenic, I guess, selenium are on their own, but quite often, remember, let's get our periodic tables out. You're going to need those today for a lot of things, actually. But quite often in the top of your periodic table, you have a list of elements there, right? And we, of course, call that Hofbrinkel in some cases, or I like to call it I have no bright or clever friends, people stupid, yes? So remember, when we're doing those elements, when you're walking down the street and you're like, hey, I sure could use some oxygen to react with my carbon to give me some carbon dioxide, well, that oxygen comes in 2s, yes? Okay. Or if I'm walking down the street and I grab a scoop of sulfur, those sulfurs come in 8s, all right? And they're on the top there for you. They're listed there. So if you're doing one of those non-metals, you have to use that molecular element, right? I have no bright or clever friends, people stupid, or Hofbrinkel P4S8. Okay, so that's what it says right here in this section here. The states of the element are found on the periodic table. So we know we talked about this yesterday. For you, I think the green stuff is the solids, yes. The kind of aquamarine, periwinkle or whatever, I don't know. I'm just yelling out names. I don't know what that means. But the bluish green stuff is solids, I think, as well. The blue ones are the gases, and then there's 2 there. Those are the liquids, yes? So if you're doing like oxygen, well, it's a gas, right? So we're going to put G, gas. If you're going to use some mercury or bromine, we're going to put L's there because they're liquids at room temperature, okay? And of course, we already know this, but all ionic compounds are solids, yes? So if we're trying to form an ionic compound, we're trying to make a solid here. It's going to make a solid eventually. Good? Okay. All right. We'll come back to that in a sec here. Don't worry about all this stuff here, but basically it says formation reactions are also known as synthesis, so you can write that down. I'm going to be honest with you, okay? It's true, absolutely. I'll probably never say the word synthesis again, okay? Just so you know, I don't care. We call them formation reactions. We always do. Okay, chem grade 11, grade 12, whatever, university, probably formation. All right. And basically how this works is we're going to take two or more elements to form a compound. Okay. Formation reactions are also known as synthesis. In this reaction, 2 or more elements form a compound. So for example, I'm just going to go to this sheet here because that doesn't really make sense there. So A plus B. You can just write this in there in the first little arrow there. A plus B would give me AB, for example. Okay. So formation reactions are also known as synthesis. And in this reaction type, or this type of reaction, 2 or more elements combined to form a compound. For example, A plus B would give me AB, for example. Okay. Let's see here. All right. Or, yeah. Or I guess you could say what they're trying to say is element plus element gives you compound. So I guess you could write this in the other, whatever other one you got there. Element plus element gives you compound. Okay. If you need to. All right. Now, we're going to look at this first one here. We're going to go in order with what you have here, and I might skip over some of the stuff that I have on my slides here, but we're just going to go in the order that you have here. So is that good? Element plus element compound, or A plus B equals AB, basically. Okay. The first one you have, it says, in one type of formation reaction, two nonmetals can react to form a molecule. For example, sulfur and oxygen can react to produce sulfur dioxide. So they want you to write out a word equation. Well, it's kind of already there, yes, for the most part. But basically all they're saying for the word equation, this is not, I'm going to be honest with you, this is kind of, in my opinion, I shouldn't even say this. All right, see? People at home have no idea what I just said. I said it was stupid. All right, sulfur plus, what did I say, oxygen gives me, what's here, sulfur dioxide. And that would be your word equation. Again, I'm not too, that's not really, that's fine. That's all good. But ultimately, if I give you some elements here, we want to be able to write them down chemically and then start balancing right away, kind of thing. So it says here, what's the skeleton equation? Well, the skeleton equation would be sulfur. Okay, and I want you to look these up now. So sulfur comes in 8s. Okay, sulfur is one of those molecular elements. If you look at sulfur on the periodic table, it is in that, what color? Kind of like aquamarine, yes? Well, I don't know, what color is that? Turquoise. It's in turquoise, okay? That's a real man right there because he knows turquoise, okay? Periwinkle, I know that one too. I have no idea what color that is, but I've heard that before sometime. Magenta is another one that I've heard, and pink. All right, sulfur. Sulfur comes in 8s, and it's a solid. Okay, it says so on the periodic table. Oxygen comes in 2s, and it's a gas. All right. Now, molecular compounds are a little bit hard because molecular compounds can combine together, or sorry, when we start with two nonmetals, they can combine to form, obviously they're going to form a molecular compound, yes, because we have nonmetals and nonmetals, and they're going to start to share electrons, of course, covalently bond. But the problem with molecular compounds is they can form many different types of compounds. You know, just because I have sulfurs and oxygens, they can combine together in many numerous ways, all right? So if I take carbons and hydrogens, for example, if I take carbons and hydrogens and mix them together, I can get CH4, I can get C2H8, I can get propane, butane, methane, propane, whatever, hexane, etc. There's lots of different ways that they can combine together. Okay, but so in this case here, the molecular compound, they'll usually tell you what the product is that they want you to form, because I don't really know. They can combine in so many different ways. That's why we have prefixes, right? You know, like disulfur pentaoxide was one on your quiz or something like that. Or maybe it's going to be tetrasulfur decaoxide or something. I don't know. Like there's lots of different options. So in this case, they tell you it's sulfur dioxide. And do they tell you that it doesn't tell you what this is? So I'm just going to sulfur dioxide, okay? So it says sulfur plus oxygen can react together to produce sulfur dioxide. So we run into our first issue already here. What state should I put here? Any ideas? What do you think? Well, no, it's got to be, it won't be aqueous because we're not using water here. None of these are going to be aqueous today because we're not using water to make these. We're taking element plus element. Probably going to put some heat in so we can kind of combine them together or whatever the case might be, but we're probably not going to use any water to do this today. Sulfur plus oxygen. How do we determine states of molecular compounds? The answer is, well, we usually tell you, okay, because the states for a molecular compound could either be gas, liquid, or solid, yes? So this is a gas, but you wouldn't know that. Okay, but I'm just going to leave it blank because you don't know. That's fine. Okay, molecular compounds are hard because it really depends on those intermolecular forces, if you remember that term, on how well they stick together. And we don't really know that yet. So, and even in grade 11, we wouldn't know that. And even grade 12, ish kind of thing, right? So that becomes a little tough. So we're just going to actually leave it blank. Okay. This would be what we call the skeleton equation. This is kind of probably where we should start. Okay, honestly, I'm not too big on the word equation, don't really care. But if it says sulfur plus oxygen, I want to be able to write S8 plus O2 gives me sulfur dioxide. Then, of course, in the next part here, it says we want the balanced chemical equation. Honestly, this is the same as that, in my opinion. I would do this, and I would probably not write another one out, of course. I would just balance this, yes? So if I was balancing, I'm going to give you a little tip here. Obviously, what do we usually do? What do I usually tell you? Don't start with oxygen, right? And probably start with what? Sulfur, yes? Not only because it's on the left, and I kind of do things left to right, but also because it's got the most. So if it's got the most, like S8, you probably want to start there. Or if you got a P4, bingo. No, that's B4. Never mind. If you got an S8 or a P4, that's probably where you should start, because that's the one that you're going to have to balance because you have the most of them, right? So in this case, I say, well, S8, okay, S8. How am I going to get 8 S's? I'm going to put an 8 in front, okay? How many oxygens do I have on the right-hand side? How many? Just yell it out. Don't be shy. How many? Quickly. Come on, math. Yep. Let's try again. How many oxygens do I have on the right-hand side? 16. 8 times 2 is 16. No, they're on this side. 16. How many do I have to put on this side? What's the number I need to put for the coefficient? 8 times 2 is 16. Yes? And there's your balanced chemical equation. That's a formation reaction. Okay, so if it says, hey, I'm going to take this element plus maybe even another element to get this compound, that's formation. When I start with elements and I make a compound. Whether it's nonmetals, will make molecular compounds, right? And then we'll talk about other options here as well. Okay, good? Questions, anyone? Now the next one here says a metal and a nonmetal can also react to form an ionic compound. For example, sodium and chlorine can react together. Okay, so let's take a look here. I'll do that one too. But sodium, I guess I'll write it out here real quick. And chlorine gives me, now, in this case here, I'm just gonna, and it tells you actually to form sodium chloride. But this is now different. This is now a metal and a nonmetal. So if I look here, sodium, that is a solid, yes. Look it up on your periodic table. It's in green, light green. And chlorine, chlorine is what? Cl2. It's one of those molecular elements. And what state is that in? Gas. Okay. Now, here's the thing about a metal and a nonmetal. I probably wouldn't even have to give you the rest of this because you know that if I combine sodium and chlorine, we are going to get an ionic compound, yes? Metals and nonmetals. So if it's a metal and a nonmetal, we use, of course, now charges, yes? To get that, there's only one thing it can form because this is going to want to lose electrons and these are going to want to gain electrons, yes? Okay, to give you sodium 1 plus, chloride 1 minus, yes? Sodium chloride, metals and nonmetals, okay? And I'll write that up here. It actually tells you this in the notes as well, sodium chloride, okay? What state do I put on sodium chloride? Yeah, always. Ionic compound, yes? Ionic compound, we're going to put solid there, okay? These metals and nonmetals always work out better for us, okay? So you might say, how is that going to, how could you take a solid and mix it with a gas and get another solid? Well, you'd have to melt them down, right? You'd have to put in some energy for this to happen. So you'd have to maybe melt the sodium down, okay, and then mix it with some gas, and eventually you'd let them re-solidify and you get some sodium chloride. Okay, so that's that part there. Before we do the next part here, which is that'd be, I guess that's your skeleton equation, yes. Before we do the balancing, I have a skill testing question for you. We already talked about it today. What is the charge on this sodium right here? What is the charge on that sodium? And you should not be looking at your periodic table right now, because you should know. Yep. Yes. Thank you. So this has no charge. This is just pure sodium. Walking down the street, hey, sodium, right? Right? Okay. What's the charge on this chlorine gas here? What's the charge on those? Anyone else? Okay. Neutral. No charge. Okay. Now, what's the charge on this sodium here? Page. Yeah. What's the charge on the chlorine, or that well, what's the charge? I guess I should, what's the charge on the chloride, which kind of gives it away? Yeah. 1 minus, right? Okay. That's important. All right. We have to know that. When you're walking down the street, sodium by itself is neutral. Yes? There's no, you don't have to, you can put those there. I'm not going to do that again. I just want you to know that. Like, sodium by itself, look, if sodium's by itself, right? If this was just by itself, it has to be neutral, because how does sodium become sodium 1 plus? It has to do what? Tell me. How does sodium become sodium 1 plus? It has to what? Has to lose an electron. How is sodium by itself, just in this little beaker right here, let's say, for example, or that little separate thing there, how is it going to lose an electron? It can't. Where's the electron going to go, right? So we have to remember we're starting with neutral elements here. Sodium's by itself, it's neutral. Chlorine, now I got a container of chlorine here, and it's by itself. How is it going to gain electrons? From where? It's by itself. It's chlorine. It's by itself. It can't gain electrons. It's not until you react the two together, yes, that's what we're doing here, that this loses electrons to that, yes? That's when the chlorine atoms say, hey, I want your electrons, I'm going to take them. And sodium's like, yes, please do, because now we have octets, yes? Okay. That goes back to the Bohr diagrams you guys used to draw, and you'd have Na1 plus on the outside, and you'd show the arrow going over. That's what we're doing. We're doing the chemical reaction to make sodium chloride, all right? Now, is that good? If I was going to balance, okay, well, again, up to you where you want to start, but there's Na there, and there's Na there, so that's good, right? And then there's Cl2 here. There's only 1 here, so I'd put a 2 there, and then I have to go back and fix my 2 there. Yes? Right? Questions, anyone? Yep. Oh, stretching. All right, good? Okay. We'll do a couple more here, but okay. The next one here says, and again, I think we're just going to skip this word equation thing here because, well, maybe not. Maybe I lied. Write the word equation and balance chemical equation for a reaction of iron and chlorine. So iron and chlorine, okay, is going to give me something. Now, this one we do need to talk about here. So here's the deal, okay? Iron plus chlorine. So before I give you the product here, I'm actually going to start here. So I would say, okay, well, iron comes in what state? Periodic table. Solid. Most of the metals, remember, are solids, yes. And chlorine, we already did that one, that's a gas, gives me what? Okay. And would you agree that we're probably going to get something like iron chloride, yes? Does that make sense? Okay. However, here's the issue. Iron chloride. Is that okay for everybody? Iron and, we're going to have an iron. We're going to have some chlorine. Chlorine's going to gain the electrons. Iron's going to lose them. But iron comes in more than one charge. Yes? So which one do we use? And this is going to be important for the rest of your life here. We always use the first one on the periodic table. So when you take a look at iron, find it. I shouldn't say we always use it, but because we're trying to form some iron chloride, we need to know that iron comes in a 3+ and a 2+. 3+ comes first on your chart, yes? It's the first one, so it's the most common one, okay? So we always go with that, iron 3 chloride, okay? So we'll do that. And then, of course, here, we'll put iron 3 chloride. Iron's a 3+, chloride's a 1-. We swap and drop, and, of course, we get that. And the state, of course, would be, yell it out. Thank you, solid, okay? Because we're trying to form an ionic compound, all right? So, great. Balancing, okay? Well, iron is good with iron. And then usually with these types of questions, we have Cl2, we have Cl3. We talked about, I think we talked about yesterday, lowest common multiple, is that right? So basically, what's the lowest number we could get on both sides? And that would be, of course, 6 in this case, yes? 2 and 3. So I'm going to do the old, I like to call it the switch. When I see 2 and 3, I just call it, I don't know why, I just name it, I call it the old switcheroo, where I just kind of flip the numbers. So if this is a 2 and a 3, I got to do a 3 here and a 2 there, basically, to make 6 and 6, okay? Again, if you're doing 4 and 6, then 24 is not the lowest common multiple. Okay, so just to be aware. Okay, which means I have what? 2 FEs, so I'm going to put a 2 there. Yes? Good? Questions, anyone? Okay, yep. Because this isn't an ion. This is neutral. That has no charge right now. Yeah, just iron. No charge. Okay. All right, good. Okay. I think I had one on here that said something about magnesium and oxygen. I don't know if, I know that's not on your chart there, but do you want another example, or are we good with this kind of thing? What do you think? Yes, no? It's up to you. I mean, I can make up any one. Good? Okay, I think I had, what did I have here? What is this? Okay, that's that first example there. Magnesium and oxygen, for example. I don't know if you want, you maybe just, I don't know, it's up to you. If you want to write it down, fine. If not, I don't know where you're going to write it down because you don't really have a lot of room there. But, magnesium and oxygen, right? And again, in this case, we're going to get magnesium and oxygen together, which of course would be magnesium oxide, yes? So magnesium oxide. 2+, 2-, swap, drop, and reduce. States, this would be a solid, this would be a gas, and this would be a solid ionic compound, right? And then balancing wise, well, probably start with a 2 here, and then a 2 here, yeah? Okay. So if you're combining magnesium and oxygen together, we know the product is going to be magnesium oxide. And again, we know it's going to be a solid. We use charges, so we know the formula. Molecular ones are going to be a little more tricky because, again, we're not going to know what the formula is probably. Like if I just combine nitrogens and hydrogens, what would the formula be? What would you get? Most of us wouldn't have a clue, because they can combine together in so many different ways. So that's where it becomes a little tricky. But with ionic, they work out well. We did that one. What else did we do? Did we do that one? Yeah, sure did. And then we did that. Don't forget about Hofbrinkel P4S8. Okay, we're going to do decomposition reactions next here. I think, let's see. Yeah, we talked about all this already here. Basically, just remember to refer to the states for the elements. Don't forget about multivalent ones. Okay, we want to pick the first one probably. On the back side, here we go, and then we're done. So basically, what we're going to say here is a compound now. So for decomposition, we're going to do the opposite. We're going to take a compound and break it into elements and elements. Or if we had, for example, AB here, we're going to get A plus B. Okay, kind of deal. It's the complete opposite of formation. That's why we do these on the same day, because look, it's exactly what we just did. Okay, just other way. Do not try to do this. Please don't try and use backwards arrows. There's no such thing as a backwards arrow. Okay, I don't know what that means. All right, there's only one way we go. We go left to right. So there's no such thing as a backwards arrow. Don't write it down and be like, oops, and then switch it, just erase it, because I'll mark it wrong. Okay, here we go. Like I said, it's just the complete opposite. So now we're going to start with a compound, and it's going to break up into elements. So we start with what? Aluminum chloride decomposes to form aluminum and chlorine. Write the word equation. We're going to skip that. And balance chemical equation for this reaction. So aluminum chloride, ionic compound. So we're going to use charges, yes? 3 plus, 1 minus, swap and drop. Yes, aluminum chloride looks like that. Okay, and again, if I'm going too fast with that stuff there, you might have to slow down a little bit and say, okay, you got to look up aluminum. Aluminum's a 3 plus, chloride's a 1 minus, swap and drop, right? Aluminum chloride gives you, of course, it's going to break into its elements. What are the two things that make up aluminum chloride? Aluminum and chlorine. And chlorine happens to come in twos, though. Okay. Again, we're going to want to use states here because we know how to use states for the most part. Solid, ionic compound, metal, solid, gas, chlorine. Okay? Like I said, it's just the complete opposite. We're going to start with the compound and write the elements instead. Balancing, let's see. Where would I want to start? Probably here, yes. Aluminum's good, but chlorine's not. So we'll do the old switcheroo thing, or lowest common multiple. So I'm going to put a 2 here to get 6 chlorines, and I'm going to put a 3 here to get 6 chlorines, yes? So I'd probably start there with the chlorines. And then how many aluminums do I have? 2. So let's put a 2 there. Okay? Good? All right. Questions? Anyone? Okay. The next one says, let's try and write the word equation for the decomposition of water. All right, well, water we know hopefully is H2O. Now, we do know this particular molecular compound. Okay, water's a liquid, yes, at room temperature. So we do, we will put that there, obviously, because we do know that one. Now, like I said, carbon dioxide, most of us probably know it's a gas, so that's probably fine. We could probably put a G there, for that. But in this, there's a couple common ones, but most of them, like sulfurs and oxygens, we don't really know what's going to happen there. But water is going to decompose. What does water eventually decompose into? Well, the first thing you'd say is, well, does this really happen? Well, water, if you put heat into water, by the way, how do you decompose compounds? You usually put heat into them, yes, to try them break them down into elements or whatever. Usually it takes a lot of heat sometimes to get that to happen, because the first thing that's going to happen is you're going to change water liquid into what? Water vapor, water gas, yes? And then you'd have to continue to heat it to get those covalent bonds to break in the gas, all right? So eventually this would happen. You'd get what? Hydrogen comes in twos, and what? Oxygen, yes, comes in twos. And then you could say, that's my skeleton equation, yes? Okay? Hydrogen and oxygen. You just have to say those elements by themselves. And of course, if they're an element that's in the top there, one of those ones that we put on the top right, the very top of your periodic table, then that's the one we want to use. If we're talking about phosphorus, we want to use P4, okay? Balancing, well, 2 hydrogens, that's good. 1 O, 2 O's, so we got to put a 2 there is the only thing I can do to it now. And then, of course, 2 hydrogens, 2 H2s, 2 H2s, okay? And we'd get something that looks like that. Is that good? Okay. Again, it's just the complete opposite of what we just did with formation, yes? Okay. Those are 2 of the 5 reaction types already that you now know. Okay. Questions, anyone? Yeah. Well, it becomes hydrogen and oxygen. And then after that, that's pretty much it.